In a previous video I have shown how this Softrock was calibrated in Linrad using this function generator. Now I will evaluate that calibration by use of a proper pulse generator, this thing. I will compare them by use of this oscilloscope. With the attenuator here, the signal level is set to give the same signal strength and the same pulse repetition frequency in Linrad. And the input on the oscilloscope is 50 ohms, just like the Softrock on 14 megahertz, where the experiment was done. And the oscilloscope is set to display the two traces, and it triggers on each one. So here you can see the square wave, but the pulses are invisible. I have to expand the time scale. It is now 1 millisecond. And now we see nothing. I need more brightness. Here. At 10 nanoseconds, you can see that the proper pulse generator has an amplitude of 1 volt, while the function generator has an amplitude of a little bit above 3 volts. But they give the same signal level at 14 megahertz. This is the interior of the proper pulse generator. It has a 555 here. The switches and the potentiometer can set the frequency. It's followed by a frequency divider, 74 AC 74, to make sure we have a square wave with the same length of high and low. And then it's followed by a driver. In this case it's a 74 ACT04. It could be a 74 AC04, but I take what I have in the junk box. Then the output is taken through a capacitor and a resistor to ground. That's why we have a pulse with a fairly short length. And every second pulse has the opposite sign, but that doesn't matter at all for the calibration process. Here Linrad is running with the function generator as input. Select the signal and we can see the noise level is at 72 dB. And enable the smart blanker here. It goes down to 58 or something. To understand what it means, I have to tell Linrad I'm an expert. That's S. And I change to expert mode, yes. Font scale, I stay 2. And yes, and we don't block anything. Specify screen in pixels, yes, and I make it a little bit wider, 1400 by 768, and normal priority, and no auto start. And save. And now I have to exit, escape, and restart. And we have a little bit more screen width, and go for D, and I can make this And we have the noise blanker running, and I have to select some reasonable frequency. Start the oscilloscope. That is the expert feature I was looking for. You see a lot of noise. Disable the blanker, and you see the pulses. I can show the effect of the dumb blanker. Click the yellow here, and you see it cuts fairly large holes in the time domain. It is 5%, but enabling also the smart blanker, that wins over the dumb blanker, and there are nearly no holes cut. But the noise level doesn't change, although near the center it degrades, and at the edges it improves, but these are very small differences of no significance. Now I disconnect the function generator, connect the proper pulse generator. And after the transient went away, you can see that the center region is now quite different. Select the frequency and enable the smart blanker. And now it goes down from 72 to 40. That is 32 dB about. Not too bad. And you can see the pulses are gone more or less completely, but we have some odd phenomenon that every second pulse is high or low. This phenomenon is created by the calibration function not having the phase correct. So high frequencies about near the corner here, 45 kilohertz perhaps, and 45 kilohertz here, they don't have the proper phase relation. That's why we see a fairly strong signal near the Nyquist frequency. Every second point differs from the neighboring point. This is normally corrected by use of the remove the center discontinuity, but that doesn't work in this radio because the center discontinuity is so wide. It is affected by the frequency response of the Softrock. I will now do calibration with the signal from the proper pulse generator. That is X and calibrate and B, and then I take the signal as it is first, that is enter, and clear the RAM memory from the old, that is A. So now it is the uncalibrated Fourier transforms we see. I go over to the time domain to look at the pulses in the time domain. That is T. The pulses are here, very small. I increase the level by pressing plus many times. 1, 2, 3, 4, 5, 6, 7, 8, maybe. Yeah. And here we can see the fall off that belongs to the center region of the hardware, how it falls off and about this far. And the variations here are partly because of the previous pulse, partly because of noise. But I magnify again. You can see that there are zeros from here up to this point. From here to here is a cosine square window. That is to avoid the click from switching in a DC component here. And then in the same fashion, the signal is brought down to 0 from here to here, also with a sine square function. That means that the effect of limiting the time range overlaps with the shapes of the pulses themselves, which are this form. This is not acceptable. With this hardware, one has to use a lower pulse repetition frequency. X, calibrate, B, and I make the pulse repetition frequency. We had 380 Hertz. Let's make it 100 Hertz about. Here. Press enter. And now Linrad is collecting the Fourier transforms. I press T to look at the process in the time domain. Plus, 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 something like that. And one more. Or even more. And this does not look right because I forgot to clear the RAM. These are the pulses, the true pulses. The artifact from the incorrect calibration that was visible here is gone. And you can see the effect of the 50 Hertz from the sound card traveling slowly. That will average out in the average of transforms. But it's necessary to not trigger the pulse source on the mains frequency, because if one did that, the interference would stay at the same position relative to the pulse, and that would generate incorrect calibration. So look at the frequency domain. And now the gain is very high. I have to bring it down, minus 8 times. Now 5,500 pulses, that is a lot. U. This is the correction function that Linrad needs to apply, and it has a discontinuity here that has to be removed for perfect operation. We can see also the yellow curve that shows the difference between the amplitudes we actually have and those amplitudes we need. And of course, at 0, at DC, this is infinitely high. That's absolutely not acceptable. But the first part of this is the high-pass filter inside the Softrock. It is not desirable to have it there, but it can probably not be removed without having problems with the blanker operation. So So this is a peculiarity of the Softrock that other direct conversion receivers don't have. It's a very wide range of signals that is not allowed into the digital domain. I accept this. Why? And then save. Is X and B to go back to the processing screen and select the frequency. The level is now about 37 dB when the blanker is running. If I disable the blanker, the level is 68 dB. The noise level is lower now than before because the pulse repetition frequency is now 4 times lower. That is 6 decibels. If I disconnect the pulse generator like that, the noise level drops by maybe 3 dB. So this very strong pulses that without the blanker are at 68, 67 maybe, they only cause a 2 dB degradation when the blanker is running. Looking here, you see there are some errors. There is a signal on the Nyquist frequency. We can see it here and here. And there is also some error near the center, which you can see as a curvature like that, up or down, both before and after the pulse. When I switch off the pulse generator again, you can see there is a problem here also. I don't know the cause of it. It looks like a problem with the sound card. But here you can see it is a little bit more when the blanker is running. It's not bad, however. I can increase the pulse repetition frequency. Now we have bad interference. And if I disable the blanker like that, you can see the level is 75 decibels. I have a 35 dB improvement and the remaining interference is 5 dB. And here I can also enable the dumb blanker and set the levels a bit low, like that, and gain another dB at only 2% cutaway pulses. If I increase the pulse amplitude by 10 dB, like this, you can see it doesn't work so well anymore. Something goes nonlinear inside the Softrock. I can reduce the level by 10 decibels instead. And then disable the blankers. And you see now the smart blanker, and switch off the pulse generator, and it's only 1 dB. So I have an improvement of 30 dB, but the remaining interference is only about 1 dB. as you can see here, maybe 2 dB. So the blanker is not properly calibrated, it's only the first step, but even so it is fairly efficient.